and my PhD is focused around the obtention of robustness certificates for object detectors and networks that perform semantic segmentation. So about adversarial robustness, similar to what Arthur said before, we have a problem when we use deep neural networks, is that their predictions are untrustworthy in the sense that they can vary drastically under minimal adversarial perturbations that are imperceptible to the human eye. And so that is something we're particularly interested in if we want to deploy models in safety critical domains. And so the main proxy that scientists use to develop adversarial robustness methods is to use classification tasks, as they are the prime example of what could go wrong in terms of adversarial robustness. So we try to enforce robustness locally around predictions. So this work I'll present is about semantic segmentation. So you can see on the image behind me that semantic segmentation is the task that corresponds to assigning each pixel to a class. So that class could be human, car, plane, background, anything. And so in this recent work that I'll present as a poster, we provide adversarial guarantees in two different scenarios. Either we want to certify which adversarial attacks could reach a certain performance threshold. Like, I want to have certified that my system will have an accuracy that is superior to that threshold. What is the level of noise that it could endure? Or we can do the inverse, which is to determine how much noise we need to reach another threshold. So basically you have those two sorts of different questions that can bounce around. And so we provide a framework which is agnostic from performance measures and that allows for arbitrary degradation objectives. So importantly, what we use is a Lipschitz condition on our networks. So we use special networks which allow the output perturbation to be bounded if the input perturbation that's applied is bounded. So in the sense of semantic segmentation, the actual related works usually mostly use randomized smoothing methods, which are probabilistic methods, which ensure the invariance of pixel predictions. And so basically what you're going to do is run a network n times with different noise values, and then you're going to compute a number of p-values, apply a correction, and that's very costly because usually you could do that in classification. That would work. You'd have a certificate that holds 99% of the time, except you've got huge images, and so you've got to make that certificate hold such that that holds for all the pixels in the image. So it's power of the number of pixels, which is very problematic. So this is the main problem, but it also means that you need way more inferences to make this system useful when deployed. So essentially, no methods ensure robustness at deployment in a real-time manner, sorry. So what we use is that previous Lipschitz condition, and we essentially develop a whole new brand of models which are deep lab based and which have Lipschitz properties, and we formulate our performance guarantees in terms of robustness certificate. So basically the intuition is that if I can modify a pixel, I can modify n pixels, and so that sort of becomes a knapsack problem where each pixel I could modify has a cost, which is its robustness radius, and each pixel I could modify could give a profit in terms of adversarial objectives. That means I could diminish the performance by X amount, and that would require this amount of perturbation. And so we basically devise different efficient strategies to treat the pixel accuracy, IAU, false negative rates, etc. And so the results of this paper are basically that since we avoid this sort of probabilistic computation for all the pixels in the image, we have way faster networks when we evaluate at similar performance. So for the same performance, we'll basically be either 2,000 times more efficient at inference time or 600 times more efficient at inference time, leveraging Lipschitz neural networks. So that's it for me, I think.